Welcome back to my channel. In this video, I'm going to show you the complete solution to 2020 Time Zone 0 Higher Level Paper 1. No bullshits, let's go. Question 1 is a study of the units conversion. Let's begin with the energy stored per unit volume. It's joule per meter cube, where joule is the work done, which is Newton meter divided by meter cube. So after simplifying, it is Newton per meter square. Newton per meter square is equivalent to force over area, which is pressure. The answer is D. In question 2, you got an object of 8 kg, which means it is under a weight of 80 Newton. At the same time, there is an upward drag, and the drag's magnitude is 60 Newton. To conclude, right now, the net force is 20 Newton. And because of the Newton's second law, net force equals to ma, so we have 20 equals to 8.0 kg times A. A is equal to 2.5 meter per second square. B is the answer. Question 3. We have an object in translational equilibrium, which means the net force on these objects is 0. And they are all lying on the same surface. This is known as coplanar forces. And their magnitude are 3 Newton, 4 Newton, and 5 Newton. Statement 1 suggests that all the forces they are perpendicular to each other. Can these three forces be perpendicular to each other meanwhile they are lying on the same table? Let's take a look at this drawing. There could be three forces creating each of the angle being 120 degrees. When arrows are perpendicular to each other meanwhile they are coplanar, the only way to achieve it is to create 4 arrows so that they are all perpendicular to each other. So statement 1 is wrong. Statement 2 suggests that no matter is it the 3 Newton force, 4 Newton force, or even the 5 Newton force, they are all going in the same direction. This will give you a net force of 12 newtons. It is non-zero. If it is non-zero, then it is not in translational equilibrium. So statement 2 is correct. Statement 3 is true as well because vector sum of the forces, which means the net force, should be 0. Then we choose option C. Question 4. An object is falling from a column of 20 meters and it was thrown downward at 6 meters per second. When it hits the ground, it is moving at 20 meters per second. Let's take a look at the total energy at the top. It is GPE and KE. GPE is mgh, KE is half mv squared. Mass is 1 kilogram, G is 10, H is 20. And then mass is 1 kilogram again, and the speed is 6 n squared. So the energy at the top is 218 joules. At the bottom here is once again GPE and KE. The amount of GPE should be 0 because it's on the ground, the height is 0. The kinetic energy is half times its mass times its new speed square. It is 200 joules. Why the energy at the top and on the ground they are so different? Because of there should be some energy transfer to the air particles. The amount of energy lost is difference between 218 and 200, which is 18 joules. So the answer is B. Question 5. We have a car starting from rest, which means its initial velocity is 0. Next, the driving force is constant as well. Therefore, you can use Suvat equations. There is no air resistance as it travels. The question is, what is the power developed varying with the distance is traveled? Then let's begin with P equals to Fv. This is an equation for the mechanical power, and you can find this in topic 2.3. Next, we replace V with something else. Note that we can use Suvat equation now, so we can use V squared equals to U squared plus 2AS. Therefore, we can replace the V with square root of U squared plus 2AS. U is 0, so the equation is simplified as 2AS. And I would put the S out of the rest, making it bracket F times square root 2A times square root S. Why do we bother to make this change? Because I want to highlight everything in the bracket is a constant. In this case, we can conclude P is directly proportional to the square root of distances traveled. In other words, if you draw a graph of P against square root S, it should be a straight line graph. Therefore, the P against S graph is a curve. It is a non-linear graph. And the answer is the power should be increasing non-linearly. In question 6, we have an object of 2m and it is moving at 3v towards a stationary 4m object. Then, after they collide, they'll be moving together, which means it's a 2m and 4m combined objects and it's moving at a final velocity, unknown. To conserve the momentum, the total momenta before collisions and the total momenta after collision must be the same. The total momenta before collisions was 2m times 3v. It was 6mv. Then after the collisions, it will be 6mv again. It is 6m times 1v. So the final speed is 1v. And how about the change in kinetic energy? What was the kinetic energy before collision? The Ke before collision was half times its mass times the speed square. So it was 9mv square. But after the collisions, it will be half times the mass times the v square. So it is 3mv square. It's reduced by 6mv. And the answer is B. Question 7 is about the assumption of the kinetic model of an ideal gas. For instance, you have a container here, and there is a gas particle moving towards the right-hand side. After it bounces with the wall, it collides with the wall, then it will go back to the left. And there was a momentum pointing to the right-hand side, another momentum pointing to the left-hand side. We shall denote them in opposite direction by plus and minus. Obviously, there is a change in momentum here. Because of the change in momentum, there is a force. And because of the force is exerted on the wall, there is a pressure. And this is the gas pressure. In other words, the change in momentum is not negligible, so as to obtain the pressure acting onto the wall, and therefore C is the answer. In question 8, we are going to compare the gas and liquid density. In a liquid, we label the side of it Bs, and you can see S is actually R and R together. So the side of D square is 2R, and which is the diameter. We label this one as S subscript L, stand for the side of the liquid. Similarly, on the right-hand side, this side, it is the side of the gas, and it is the unknown distance. Let's refer to the question provided information. Density of liquid to the density of gas is 1000 to 1. And it is also the inverse proportional to their volume. How about volume? How is it related to the sides? Just like math, geometrically you can tell it is the ratio of their sides cube. Therefore, now you can conclude the side of the gas should be 10 times of the sides of the liquid. So the sides of the gas molecular structure is 10 times B. The answer is B. Question 9. It's a very common question about ideal gas. You have two containers and you are going to connect them together. And the following method is, to be honest, pretty long, but the benefit is it's very organized. So it's almost guaranteed as long as you work out the math carefully, you can get the correct answer. Let's start with drawing a table denoting container X, container Y, and when they are combined, container XY. In this table, we are going to study all the features of an ideal gas, which includes the pressure, the volume, the number of mole, and the temperature in Kelvin. The pressure of container X, it was 100 Pascal. Y, it was 50. Volume of X, it was 4 meter cube and 6 meter cube for Y. The number of molecule in X, let's say it is n subscript X and n subscript Y, as they are not given with their exact values. And the temperature, they were held the same. And even the temperature was held throughout the experiments being the same temperature as well. What is the number of mole when they are combined? As this is an isolated system, then the number of gas will therefore be the same as they combined. Volume is combined as well, 10. And the question is the new pressure. This is the unknown. You can see that the connection between the left-hand side and the right-hand side is clearly their number of moles. So let's begin with the ideal gas equation. PV equals nRT, and when you make n being the subject, it is PV over RT. Therefore, the connection right now is we have n sub x plus n sub y being the new one, n sub xy. It is the pressure of X, therefore 100, times the volume of X, therefore 4, divided by R and T. 50 times 6 for Y, divided by RT. On the right hand side, you have pressure of XY times the volume of XY. It's 10 divided by RT. After rearranging, you should get pressure of XY being 70 Pascal. The answer is A. Question 10 is a pretty easy one. It begins with a simple harmonic motion, which means we should start with acceleration is proportional to the negative of x. X stands for the displacement from equilibrium points. If you want to get the maximum acceleration, there should be a maximum displacement from the equilibrium point. Then the answer is D. You need to get the maximum acceleration when it is at the extreme position, the furthest point away from the equilibrium point. Next, question 11 is about the study of phase difference of a wave. Let's build up the table of the connection between phase difference in degree, in radian, as well as their distances. If the phase difference is 0 degree, then it will be 0 pi radian or simply 0 radian apart, and the distance is exactly 0 meter away from each other. What about when they are separated by one cycle, therefore their distance apart is 1 lambda, 1 wavelength? It is exactly 2 pi radian apart and 360 degree apart. And the other very common value is when they are 180 degree apart, it will be 1 pi radian apart, and the distance is half of a wavelength. Now, the given information is when they are 60 degree apart. it should be pi over 3 radian apart. And the distance should be how many wavelengths? It is 1/6 of a wavelength, and it is converted to 0.050 meter. To continue, we build up an equation over here. It's 0.050 meter, therefore lambda is 0.30 meter. Having the lambda, we can get the speed of the wave using v equals f lambda. Frequency is 500 and the wavelength is 0.3. Therefore, the speed of the wave is 150 meter per second. The answer is C. Question 12. These lines, they are the wave fronts. Therefore, in order to show their ray, you must draw it by yourself. And let's begin with the normal line. The wave fronts and the ray, they are perpendicular. So the approaching ray is in this direction such that it is perpendicular to the incoming wave front. The refracted one is over here, so that it is perpendicular to the emerged wave front as well. The angle of incidence is over here. It is 45 degrees. The angle of refraction is here. It is 30 degrees. So, using the Snell's law, we can get N of Q divided by N of air. It is angle of air over the angle of Q. N of Q is the unknown, but N of air is 1. It's something you should memorize. It's not given in the exam. The angle in air is 45 degrees. The angle in Q is 30 degrees. So the answer is B. In question 13, there is a pipe and we are going to create a second harmonics in this pipe. It will be going in this pattern. Position P and Q, they're separated by one node. Every point, literally every point on the yellow and on the green, they are separated by a node. Their phase difference is gonna be the same, which is 1 pi radian, as they are always in anti-phase. Question 14, we have a metal wire. The target is to get the currents per unit area, which is I over A. Let's begin with the equation I equals NVQA. We rearrange the I over A be the subject, then we have NVQ. N is known, Q is known, leaving the V unknown yet. So the answer is B. Oh dear, in question 15, you have another complicated circuit. It is the Kirchhoff's law. To facilitate our teaching, I'm going to add color to it. I will make it green for the cell, blue for this resistor, and finally red for this resistor. We are not going to study the rest because according to the question, we are studying the loop WXYUW. And this is the external loop. For all closed loop, according to the Kirchhoff's law, it should be conserving its energy, which means the voltage gain and the voltage lost, they are the same. The voltage gain of this circuit is the voltage of green, which is the EMF, then followed up by the first voltage drop, which happens at the blue one. And it's between point W and X. Next voltage drop is the red one. It is between X and Y. That's how we have the initial equation created. But what's next? Next, we are going to rewrite the blue voltage and the red voltage in terms of I and R. To do so, we need to rewrite them using the Ohm's law, which is the current times is resistance, both for the blue and the red. The current of Wx is clearly I2 is given in the question. And the resistance of Wx is simply R. So there is nothing tricky here. The problem is we don't know the red currents. How do we denote the red currents? We can study the junction X. At junction X, because of the conservation of charge, the currents flowing into the junction and the currents flowing out of the junction should be the same. Then we have I2 flowing into the junction, the same as the current flowing out, which includes I3 and the unknown current. So the unknown current is I2 minus I3. This is the current at this point. Next, we substitute I2 minus I3 here. And then the resistance of XY is R. Pretty much is all set. The rest is simplifying the equations. You have I sub 2 times R plus the I sub 2 times R again and minus I sub 3 times R. So the answer is 2 times the I sub 2 R minus I sub 3 R. The answer is D. Question 16 is about the relationship between resistivity and resistance. Let's begin with the equation resistivity. It is RA over L. A is the cross-sectional area, and we can assume this is a circular wire. Then it will be pi r squared. As r and pi, they are constant, so it is bracket r pi and then r squared over L. It's proportional to r squared over L. The answer is D. Question 17. Let's label all the given number. We have a power here, voltage here, and we have resistance here. The question is power loss. I know that it's very tempting to start with V squared over R, but stop at here. Because you must understand which P, V, and R are they referring to. And let's draw the diagram to show their relationship. There is a power station here, and coming from the power station, there is a long cable with certain resistance. This is the long cable, and for instance, maybe in the city, there are lots of power consumption, so there is a great load over there. The first value given, 250 kilowatts, is the power from the station. 250 kilowatts. Next, 4.0 ohm. It is the resistance of the very long transmission cable. Then we can put down here 4.0 ohm. Next, the potential difference is created at the power station. So the V of 25 kilovolts is off the power station as well. If you got tempted using the equation like 25,000 squared divided by the R 4.0 is definitely wrong because you are mixing with two different subjects within the same equation. So don't make this mistake. Instead, to get a power loss at the long cable, you should get I squared R. Make sure you put everything to the cable. What is the current running through the cable, which is obtained using P equals IV of the station. So you have 250,000 current times the voltage 25,000. So the current here is 10 ampere. 10 ampere current is running through the whole loop, including the long cable. We have 10 squared times its resistance. It gives you 400 watts. The answer is B. Question 18 is about the definition of electromotive force. When a cell is connected in a circuit, in a closed loop, there should be a current running through. The potential difference of the yellow part is known as the EMF. The potential difference of the green, which include the internal resistor, it is known as the terminal potential difference. In other words, back to this question, our target is to get the electromotive force only. Therefore, we should study the power supplied by the cell. Therefore, it is the total energy delivered in the whole circuit divided by the charge. And charge is the product of current and times. Therefore, the answer is A. Question 19. There is a wire carrying currents between a set of bar magnets. So there is a magnetic force acting on this wire. The force direction is predicted by the Fleming left-hand rule. This is the Fleming left-hand rule. The thumb represents the force, index is the magnetic field, and your middle finger is the current. This is exactly the same as the setup on the left. The magnetic field is going from the North Pole to the South Pole. The current is as indicated by the question. And lastly, the force is going up. So the answer to this one is A. Question 20 is about a circular motion. Here we have a mass small m attached to a string which oscillates around the straw. This small m is experiencing a net force going to the center. This net force will therefore provide the centripetal force to maintain its motion. And this is exactly the same as the tension going along the string, and the tension of the string would support the m, prevent the m from falling downwards. The downward force is big mg and the upward force is tension. Therefore, we can merge these two information together, noting that the net force on the small m is actually the weight of the big M. The net force is the centripetal force. It is mv squared over r. Note that we have two different m here. The big mg represents the weight of the big mass, and the small mv squared over r is the object that is oscillating. Next, we rearrange to get big M be the subject, that is mv squared times g over r. The answer is C. In question 21, you can see there are 4 energy states of an atom, and we are looking for an emission of radiation. Therefore, we look for a de-excitation. De-excitation, which means the electron is moving to a lower energy level. For instance, it could be moving from E4 to E3, it could be moving from E2 to E1, or it could be moving across multiple levels. It could be starting from E4 down to E1 directly. And whatever the excitation you see, there must be an energy release to the surrounding by emitting a photon. A photon, which means a radiation. Each photon, its energy is determined by the difference between the starting energy level and the ending energy level. For instance, E4 to E3, it gives you the lowest energy. From E4 to E1, it is the biggest leap and it will give you the greatest energy. Which one are we looking for? We should get the shortest wavelength. The wavelength of photon is related to its energy in this equation. You can find it in your formula sheet in topic 7. Therefore, wavelength is inversely proportional to the energy. If we are looking for the shortest wavelength, then we should get the greatest energy. So it is Hc of E4 minus E1. The answer is A. Question 22. There is a Feynman diagram, and it is part of the Feynman diagram. Let's study what are the particles on the left and on the right. UUD, it is proton and is something you should memorize. On the right hand side, you can see U took an express train to the right hand side without any stop in the middle, so as D took an express train. Therefore, it is down, up, down, and it is a neutron. Once again, proton being up, up, down, and neutron is down, down, up. These are something you should memorize. How about the one at the top? It is pion plus or pion negative or maybe pion zero. But it's not something we should consider because you can tell there must be a neutron. Therefore, only A or B. And next, we can compare the charge on the left and the charges on the right. Charges on the left, they are always proton and proton. So it must be plus 2e going to the right hand side plus 2e. Let's take a look at option A. It's plus 1e, 0e, and plus 1e. So the answer is A. Question 23 is about the history of physics. We are looking for a paradigm shift. Paradigm shift is a new concept which is brought to the common lexicon. For instance, it was a fully developed wave model. Later on, there is a photon model brought into the same field. So, statement 1 is correct. Statement 2 is not a paradigm shift, since the kinetic model was not a breakthrough or a new idea replacing the old one. Kinetic model of ideal gas is the fundamental itself, so it is not a paradigm shift. The mass and energy equivalence is a new idea, because the people back then did not imagine the conversion between mass and energy could be possible. So statement 3 is one of a paradigm shift. The answer is B. Question 24 is about nuclear physics. It's a nuclear reaction, so let's begin with the E equals mc squared. Next, we are studying the power, which means it is energy developed per unit time and is mass over T as well. The m over T is over here. It is the m over T. However, it is not in its SI units. It should be in kilogram and it should be per second. Therefore, we are going to convert 8 milligram per 1 hour into certain kilogram to 1 second. That is 3,600 seconds and 8 times 10 to the power of negative 6 kilogram. The power is E over T, and the m over T is 8 times 6 to the power of negative 6 over 3,600. C on the right is the speed of light, 3 times 10 to the power of 8, and then square. The rest is simplifying these equations. 200 megawatt. But this is not the final answer yet. Don't forget there is an efficiency of 50% only. Therefore, the useful power should be half of the 200 megawatt is 100 megawatt. The answer is A. Question 25. In a nuclear power station, there is a lot of different energy transfer. Overall, is nuclear energy to electrical, so it's very tempting to pick D. But D is wrong, because we are looking at the energy transfer by the generator only. In a generator, there are turbine, there are spinning coil, there are lots of electrical components. And it's converting the spinning rotational motion into electrical energy. So the answer is B. Question 26. It's about its temperature and intensity relationship. Let's begin with the Stefan-Boltzmann Law. P equals E sigma A T to the power of 4. Where is the intensity? The intensity is rearranged as follows. It's defined as the power over area, so it's E sigma T to the power of 4. As the two objects, they have the same emissivities, so the bracket itself is a constant. We can take intensity is proportional to the surface temperature power of 4. When the temperature is differed by 5 times, then the intensity should be differed by 5 to the power of 4 times, which is 625 times. The answer is C. Question 27. Two different simple harmonic motions, pendulum and mass spring system. The required ratio is the time period ratio. It's the time period of a pendulum and the time period of mass spring. Their equations are given in your formula sheet 9.1, so you can put it here directly without any referencing to anything else. It's L over G and M over K. Let's simplify this big fraction. It will then be Lk over mg. What is the change suggested by the question? There's only one change. The mass is half. If the mass is half and everything else is unchanged, then we can rewrite the equation as the required ratio is now proportional to 1 over square root m. M is half is making the overall fraction times root 2. The answer is C. Question 28. We are resolving two similar lights using a diffraction grating. Then the equation required is this one. The average wavelength divided by the difference in wavelength, the order of resolutions, and n, the number of slits required. Lambda is 590. The change in wavelengths, difference in wavelength is 0.59. M is 4 and then n. Therefore, the number of lines required would be 250 lines. The answer is B. Question 29. There are two different diffraction gratings, and their difference is one of which, Y, it has more lines per meter than X, which means it's just like my drawing here. There are denser slits on diffraction grating Y, and the distance between the slits is denoted as small d. The distance between the slits on X is greater. Then we can tell d of X is greater than the d of Y. And the equation for diffraction grating is d sine theta equals to n lambda. For the given same order and the same wavelength, the distance between slits and the sine angle, they are inversely proportional. In other words, Y is spreading wider. Meanwhile, X spread less. Statement 1 suggests that the slit separation on X is further apart than Y, which is correct. Statement 2 suggests that the angle between red and blue in X is spreading wider out. It is wrong. As you can see on my drawing, it spread less. Statement 3 suggests the total number of slits visible on the screen on X is greater. Is true because it spread less, everything is very focused in the center. Then you should be able to observe more pattern on the screen than Y. The answer is B. Question 30, the answer is D. The derivation are as follows. We have centripetal force, which is mr omega square, equals to mr 2 pi over t n square, which is provided by the gravitational force, G big M small m over r square. And you can rearrange to get t being the subject. Let's begin with 4 pi square over t square. On the right is G big M small m over r square. Then you will get t, it is 4 pi square r cubed divided by g and big M square roots. Everything in green is a constant. So you can conclude t is proportional to r to the power of 3 over 2. The one with greater orbital radius should give you a greater time period. Which one is further away from the star? X is further away. So X is having a greater time period. So statement D is true. Question 31 is a very tricky one. Most people will focus on the work done, greatest work done It's true that you must move across the equipotential line to give a greatest work done, but the keyword is by the gravitational force, because there are two directions of work done. It could be work done by the gravitational force or the work done by external force. If an object it is moving from the outer orbit to the inner orbit, then the gravitational force in this case is pointing inward and the displacement or the movement is going inward as well. This would give you a positive work done. On the other hand, if there is an object moving to an outer orbit, then the displacement is going outward, but the force, the gravitational force, is still going inward. And this would give you a negative work done. Therefore, we are looking at the maximum work done by the gravitational force, and we should obtain an answer which is from the further orbits to the inner orbits. There is only one option going from the outer one to the inner one. It is C, from R going into P. Question 32. You are given with a graph of electric field strength against the distance from the center of a point charge. And the area under the graph is the question here. Let's take a look at the given equation in your formula sheets, topic 10. You have electric field strength being the negative potential gradient. And I would suggest you rearrange as follows, having negative E delta R on the left and delta VE on the right. Because you can take it just like math integration. After you introduce the integral to it, then you will get the magnitude of area of the E against R graph is the potential difference. The answer is B. Question 33. A step-up transformer is used before transmitting over a very long cable. And the reason is trying to reduce the energy lost. By stepping up the voltage and lowering the current, you can have the power loss being I square R, which is I through the cable and the resistance of the cable. You successfully lower the current and you cannot change the resistance. That's how you can reduce the power loss, increasing the efficiency. 34. About root mean square value. It's about the power, current, and resistance. The average power is calculated using the RMS currents. And the RMS current is 2I square. Meanwhile, the resistance is half R. So after simplifying, you will get 2 times of the I square R. So it is 2 times of the original power. Answer is B. Question 35 is about electromagnetic induction in a coil. And I would suggest using elimination in this question. Let's begin with which axis could be possible. Now the magnetic field is going in the direction of Z and Z prime, which means the magnetic field is probably going in this way. If you spin the coil along the axis of Z and Z prime, there is no change in magnetic flux linkage. Option A is definitely wrong. The reason is, in this case, the change in magnetic flux linkage is 0. Then it will give you the induced EMF be 0. Next one, let's go back to the graph. You can see that the graph here is a quarter of a full cycle, which means it is 90 degrees and also is pi over 2 radian. Therefore, the correct answer is C. Because C is rotating at 90 degrees, it gives you a quarter cycle change. Moreover, it's rotating about an axis other than Z prime. Question 36. It looks pretty complicated at first. You have a capacitor connected to a resistor. This capacitor was fully charged and is going to discharge through the resistor. The potential difference V of the capacitor is reducing gradually. And the correct answer is C. It is the rate of change of charge. To make it simpler, it's current. The current and the voltage, they are proportional. It's always true because V equals IR, having R being a constant here. So you can draw a conclusion of V is proportional to I. Question 37. You have a monochromatic light falling onto a metal surface, triggering a photoelectric effect. The change here is the intensity of the light is increased. What is intensity being increased? It means there are more photons falling onto the metal surface per unit time. As there are more photons falling onto the metal surface, there shall be more electrons being emitted. And the kinetic energy of the emitted electrons depends solely on the frequency of the photon. Because in order to increase the energy input of each photon, you must increase the frequency of each photon. Now, there is no change in its color, no change in its frequency, and the answer is D. Question 38 is about the size of a nucleus. The diameter is 12 femtometer, which means its radius is 6 femtometer. And the nuclear radius is going as this equation. Fermi radius times the nucleon number to the power of 1/3. It is 6 femtometer equals to 1.2 femtometer times A to the power of 1/3. So we have 5 equals to A to the power of 1/3. Therefore, A is 5 to the power of 3 is 125. The answer is C. Question 39. Energy of a photon and its wavelength is related in this equation. It's given in topic 7. After a rearrangement, you should get hc over lambda. So the answer could be A or B. Next is the momentum. It's about matter wave debye wavelength. The equation is P equals to h over lambda. Therefore, it is A. However, this equation is not given. It is not given in your exam. Please remember this one. Question 40. There is a Rutherford Geiger-Marson experiment, and it's a beam of alpha particles sending towards a thin gold foil. After passing through the thin gold foil, is spread out, is scattered in a specific manner. It is scattering at a certain angle, and the intensity of the alpha particle is not distributed randomly. Instead, it's going to distribute like this one. Having the intensity on the y-axis and the angle on the x-axis is mostly going in the center without any deflection and less are scattering in other angles. Then the answer is C. Most of the alpha particles, they are found in a straight line, undeflected. This is the end of the complete solution. Feel free to leave a comment below.